In grade 11, we said that if salt dissolved in a very low amount, it was considered to be insoluble. The reason for this is that we had to draw a line between what dissolves and what doesn't. So we talked about things that dissolved to an appreciable extent. We said that if anything dissolved with a solubility less than 0.1 grams per 100 milliliters, it was considered to be insoluble because not enough dissolved for us to care about. It turns out that the solubility of things that are insoluble is best described as an equilibrium constant because quite a bit does dissolve. We care about this bit that does dissolve when we're dealing with something like lead or mercury. In a water supply, a small amount of lead or mercury that would dissolve could build up in people that drink the water over a long and extended period of time, becoming a significant concentration. So we do care about the stuff that's considered insoluble because of health implications for one reason. For example, right now in the city of Toronto, there's a whole lot of lead in the old pipes. If you're thinking back, does this sound familiar? It does. It's the same problem the ancient Romans had 2,000 years ago, and we're still using lead in pipes 2,000 years later. We've sort of stopped now and switched over to plastic, which will probably have its own problems in a couple of years. But for the meantime, though, we're trying to get lead out of drinking water again. The good news is we know it's a problem. Ancient Rome, they didn't. They would use lead pipes and lead stemware and lead plates, and all the rich people would consume the lead at various amounts. Their acidic wine would be in the lead. It would dissolve into the wine. They would drink it, and only the rich people now would have lead poisoning. Unfortunately, lead builds up in your brain. You make terrible decisions, especially when you're running an empire, and you end up having your whole civilization taken over by barbarians, who, interesting enough, adopted your customs, culture, and learning, and then continued on that way and made more advanced civilizations. But that's a whole nother discussion. If that interests you, you can read a book called The Decline and Fall of the Roman Empire. It talks about all that kind of stuff happening in a nice, concise 1,200 pages. I digress. We're looking at salts constantly dissolving and ions constantly precipitating. And this is the basis of the equilibrium that we're dealing with here. So to understand how this works, let's look at a general example. AB is our salt that is considered to be solid. It breaks apart to form ions A plus and B negative. This shows that salt is constantly dissolving in solution. At the same time that this is happening, we have the reverse process also occurring. The reverse process are the ions constantly precipitating to form the salt. Of course, the states here, aqueous and aqueous. Some textbooks will show the reverse arrow here being significantly larger, and this is to emphasize the fact that we're dealing with a favorable reverse reaction. So we said this is best described as being an equilibrium constant. Well, that's true. We have our KEQ equation as being the rate of the forward reaction compared to the rate of the reverse reaction. Of course, we're not putting rates in this equation here. We're putting in concentrations because that stems from the rate law. Now, it's a little bit strange to see here that we have this concentration at the bottom. And it turns out that the concentration that we're dealing with here is the concentration of a solid. The concentration of a solid is entirely meaningless. And it's entirely meaningless because normally in a solution what you have is you have a beaker, you have a fixed amount of water inside, and in this beaker here, you have a certain number of particles that will dissolve and be floating around. That's what concentration is, a certain number of solutes per gram or liter of solvent. When we're talking about a solid, we have a huge mass sitting here at the bottom that's doing nothing. This mass is not interacting with the solution. In fact, there's no concentration to speak of because this mass isn't part of the solution. It's just sitting there at the bottom. We can increase this mass or decrease this mass. It simply displaces the water and doesn't interact. Consequently, if we're discussing solubility, talking about the solubility of a solid is only meaningful if we don't include the amount of solid sitting at the bottom. Look at it this way. No matter how much we put at the bottom here, once this solution up here is saturated, we can't have any more dissolve. So this bottom part here at saturation becomes meaningless. So we're not going to include it in our KQ expression. That also means then we're going to end up with a modified KQ. It's going to be the product of these two things, or the product of what dissolves. So we're going to call this our KSP, our solubility product, which is really just the concentration of the two ions in solution. We have M and N values here. The M and N values would be reflected up here as well if they were part of it. And I'll put in a little A here and a little B there to show that that's important. I'm going to take a second and get a highlighter and be overly dramatic. This is hugely important. This is our new K expression for this part of the lesson. And this KSP is built on the KQ we saw before. It works the same way. The ice tables are more or less the same. Everything is the same here. Once we realize that it's the amount that dissolves that really determines the solubility product. This also means that if you have a lot of one and a small amount of the other, you're going to get a precipitate. If you have relatively equal amounts, you're going to get a precipitate because the solution can only hold on to so many ions. This brings us to our first example. Determine the concentration of silver ions in a saturated solution of silver chloride where the KSP is 1.8 times 10 to the negative 10. Any question? Our first step always is to write a chemical equation. If we're not sure what to do, chemical equation. And again, this fits in with the kind of a bigger theme. Every time you have a problem to solve, figure out what you know before you start making decisions about it. In this case here, I know that I have silver bromide and I should have silver chloride. So silver chloride is in solution. This is going to be a solid. In some textbooks, you will see a strong bend towards this being an aqueous and then breaking into its ions. It doesn't really matter. Whatever your professor tells you next year and they insist on, just go with that. It all means the same thing. The theory, though, is that the solid has to become aqueous first, then the aqueous can break apart into ions. At this point, inconsequential. So, silver ions are created in solution, and chlorine ions are created in solution. Now, if you're wondering why I used the word created, probably shouldn't have. What would be a better word? Dissociated, right. Because dissociated refers to ions that exist separating, whereas created implies that we had a covalent molecule existing before, which is not the case. So I'll pay attention to exactly how I word things as well. Now, what do? Well, we have a certain concentration of silver ions that we want to find. So as you would expect, a nice way of doing this is to deal with an ice table, and that's what we're going to need. Before we deal with the ice table, let's take a second off to the side over here and write out our KSP expression. Our KSP is going to be the concentration of silver times the concentration of chlorine. Once we have our equilibrium expression, the easiest way to proceed is with an ice table. The textbook doesn't always use an ice table. You don't need to either. For consistency, though, and to demonstrate the point that pretty much all of our problems in this whole unit are solved with ice tables, I'm going to continue with that as well. I'm going to assume that we don't have any silver, we don't have any chlorine. We're also going to say that the amount of silver that increases is going to be a plus X, amount of chlorine that increases plus X, and their equilibrium is just going to be X and X. This is pretty straightforward. If you're looking at this saying, I didn't need an ice table for that, you're right. However, there are more complicated questions where there's exponents and coefficients where the ice table keeps you from making a couple silly mistakes. So our KSP here then is going to be 1.8 times 10 to the negative 10. And this is going to be X and X. Or essentially what we're doing is we're going to take the square root of the KSP, 1.8 times 10 to the negative 10. That's squared, bring it over, square root both sides. That gives us a final concentration or an X value of 1.3 times 10 to the negative 5. Once we have that value, that's our concentration. It's the same as this value there, and we are good. So you could write a final sentence that would say something like, the concentration of silver in solution is 1.3 times 10 to the negative 5. And yes, that's exactly what it says. Finally, take a look at page 486 and answer questions numbers 1 to 4. If you don't have time to do that, or you're good with the concept, always make sure at minimum you're going through every single blue example the textbook provides. That will give you the minimum you need to be in an okay position for next year, assuming that you understand the content well.